Hello everyone. So this is a problem solving session for the course Matrix Analysis and Application. In this session I'm going to explain some theory regarding Moore-Penrose inverse. In this session we are not going to solve any sample problems this week. I will try to explain some concept regarding Moore-Penrose inverse that might be helpful for you. Okay, so let's get started. Okay, so this will be more of an interactive session, so we can discuss about the concept that you know. So can anyone tell me the definition of a Moore-Penrose inverse, what it is? Today's talk is going to be all about the Moore-Penrose inverse. Okay, so in the lectures, sir has covered some portion of Moore-Penrose inverse, but I will start from the very beginning. The first part will be the best approximations. So these best approximation problems will happen all around in geometry, in every linear algebra problem. The very simple example of this is you take a point in R2, let's say, and then consider a line, maybe any line, this line. Then give me a point on this line. I'll say this line as L. Give me a point on this line which is closest to this point, let's say P. And I want a point on this line L which is, what do you say, the closest or nearest to point P. How do you calculate this? You put a perpendicular from point P on this line, and this will be your point, right? So what I'm doing here, anyway, this line is not a subspace, but if I consider other than this line, let's see, let's make it more precise. R2, and I take the line this, let's say y equals to x or something. And if I take a point here outside this line, and I want to find a point on this line which is closest to this point, then I'll draw a perpendicular and this will be my point. Right? This kind of theory now we do best approximation of a point in a space. Okay? So for that we'll have our vector space x be or let's say v. Norm linear space, I'll define it in more general spaces. And W be a linear subspace. For any point, let's say x belongs to V, a point W in capital W is called best approximation of x in W if norm of x minus okay, I'll name this point as u. A point u in W is called best approximation of u in capital W if norm x minus u is less equal norm x minus w for all w belongs to capital W. Okay, this inequality may be familiar with to you. This is kind of minimizing the distance, right? This is what you do in here in this line example, right? We calculate the distance of this point from every point in the space. You can see which is the least distance, this distance, right? Because of the Pythagoras theorem, you can always say this distance will be more than this distance, right? This is what we are doing. We want to find this will be your point u. In this case, W is the subspace. Okay. This problem is called as finding a best approximation of a point in a space. Okay, Is this definition clear to everyone? What we are doing?
Yes, yes.
Okay. So now let's go further. Okay. Now let X be your space Rn and W be a subspace of Rn. Since W is a linear subspace, X is a finite dimensional space, I can find an orthonormal basis of W, right? W. If this is an orthonormal basis, you can always extend this basis to the whole space. And P. Okay. Now my claim is for any small x belongs to Rn, the vector u, which is defined as summation inner product x ui ui, I going from 1 through n, no, not n, r, because dimension of w is r. This u is a best approximation of x in w. This is what I want to prove. So let's say if that is true. So let's calculate what is norm of u minus. See, first thing is, because u1 through un is a basis of script b, what I know is for any x belongs to Rn, I can write x as summation inner product x with ui I going from 1 to n. Okay, this n is important here because the whole vectors u1 through un spans the whole space Rn, but only u1 through ur spans your capital W. Right? That's what is important here. This I know. Now calculate norm of u minus x. First thing is, what will be this vector u minus x? See, u will have the summation terms only until r, and x has until n. So u minus x will have, or I'll do x minus u. X minus u will have summation terms from r plus 1 through n. Correct? Now for any w belongs to capital W, you can also write this w in linear combination, w with ui I going from 1 through r. Okay. Now what is x minus w? You get summation. For x you have inner product of x with ui, then ui I going from 1 through n, and for w you have inner product w with uj j going from only 1 through r. Right? That means first r terms here will add up with first r terms here, and then you will get summation inner product x ui minus inner product w ui I going from 1 through r, and then the left out terms. Okay. Now what is norm of x minus w, which is norm of this first term. Okay, these scalars I'll call by alpha I. These scalars are represented by alpha I, where I going from 1 to r only. This is norm of summation alpha I ui, I going from 1 to r, plus summation this inner product of x with uj, j going from r plus 1 through n. Yes. But now you observe, because ui's are orthonormal bases, this element is in u1 through is in span of u1 through ur, and this element here is in the span of ur plus 1 through un. That means these two elements are orthogonal to each other, right? Hence, by Pythagoras theorem, if I take squares, this will be square plus right. By Pythagoras theorem, okay, I'll write the statement here. In any inner product space, Pythagoras theorem states that if x is orthogonal to y, then norm x plus y squared is same as norm x squared plus norm y squared. Okay, this is what I applied here, because consider this element as x, this element as y, then norm of x plus y squared is norm x squared plus norm y squared, right? But if you observe x minus u, this is equation 1, this is equation 2, then norm x minus w squared equals to this first quantity. It's something I'll call this as just some quantity, okay, maybe alpha, the big alpha, this quantity which is non-negative, plus from equation 1, what is this quantity? This is norm x minus u squared. Now because alpha is non-negative, this is greater equal norm x minus u squared, right? So what we got, this implies norm of x minus u squared is always less equal norm x minus w squared for all w belongs to capital W, right? But then this will imply u is the best approximation of x in W. Is that clear? Do you have any doubts in this theoretical result? The important thing is its application. Okay. So today's session is going to be much more theoretical, so be prepared. It's not just problem solving sessions. I'm going to explain the theory behind Moore-Penrose inverse, why Moore-Penrose inverse was needed, and what is the mechanism that is involved in the Moore-Penrose inverse. Okay. So this was the best approximation property. And for any vector subspace, you can find for any vector subspace, you take an element outside the subspace, you can find an element in the subspace which is closest to that element. Okay. What is an example now? As we take an example of R2, right? So the example that we took was a line, this line y equals to x. And then we take a point outside the line. Let's say the point is 1 0. What is this point here? 1 comma 2 maybe, or okay, let's take this point only, 1 comma 0, and I want to find a point on this line which is closest to this point. Any guesses what this point can be? Okay, any guesses for this point? Okay, I'll draw it maybe more precise. This is point, this is your subspace. I want to find a point on this subspace here which is closest to this point. Any guesses what this point can be? Okay, we'll see what it can be.
1 by 2, 1.
Yeah?
1 by 2 and comma 1.
You are saying 1 by 2 comma 1. Is it? Okay. Okay, we'll see. One guess is 1 by 2 comma 1. So now what we have to do is we have W. We need an orthonormal basis for W. What is the basis for W? Can anyone tell me a basis for W? W is this line. Okay, this line y equals to x. Right? Just give me a basis for the space W.
1 1, sir.
Yeah, 1 is a basis. Now what is an orthonormal basis? It has to be it should have norm 1, right? So what you will do is you divide
1
this.
by root 2, 1 by root 2.
Perfect, perfect. This is a basis for W. So what I gave the formula before, that the best approximation of x, I'll call it as Px. Okay, Px will be a mapping. See, just keep in mind this notation. Px will give you a best approximation of x in W. So I gave the formula as inner product of x with ui, right? Summation, but there is only one term. So this summation I going from 1 to 1, what will it be? Just inner product of x with u1, then u1, right? Inner product of x is your element 1 comma 0, and u1 you have 1 by 1 comma 1 by root 2, and then also you have outside 1 1 by root 2. So here you get 1 inner product by root 2, and then the outside element is this. So yeah, it's 1 by 2 comma 1 by 2. Okay, so maybe the half I didn't listen for you. So 1 by 2, 1 by 2 is the element which is closest to the element 1 0 in the space. Okay, the subspace y equals to x. So this is how you find the best approximations. Okay, now how is this all related to the Moore-Penrose inverse? Let's see. So until now what we have is we can find element in the subspace which is closest to a given element. Okay, now consider system Ax equals to b, right? Everything in matrix analysis revolves around solving this system of equation Ax equals to b. If A is invertible, then we have x equals to A inverse b straight away, right? Nothing involved. But if A is not invertible, then what? Then we still want to solve this equation Ax equals to b somehow. Okay, we don't want to exact get to b, but we want to get as near to b as we can, right? Well, what does that mean? So this is, let's say, your space. If A is from if A is an m cross n matrix, then from where it goes? It goes from Rn to Rm, right? So now the range space of A, right? For any B, Ax equals to B has a solution if and only if B belongs to range space of A, correct? So let's say in Rm, this is the range space. Okay, maybe a different color. This is range space of A. This is the matrix A. So now If B is in here, you can get the inverse image, right? Maybe there are so many elements, but you can find an inverse image. Okay. But if B is somewhere outside here, then what you will do? Right? Then Ax equals to B does not have a solution, right? But now what you want to do is similar to the line thing. You want to find an element in this space, kind of orthogonal to this vector here. Now this element u tilde will be called as the best approximation of B in the range space of A, and then you will find the inverse image here of this element range space, and that will give you the least square solution, as it is called. Okay, this is the pictorial representation, but now I will write it precisely.
So can you repeat how can we find this
Yeah.
B outside?
Yeah, if B is outside your range space of A, what you do is you consider. Okay, I'll now just listen the next thing. Now you want to solve Ax equals to B, right? But if B,
Sir,
yeah,
so solving this equation Ax equals to B, we are finding an element in range space of A which is nearest to B outside B.
yes, you can say like that. See, you want to find first of all an element in the range space of A which is nearest to B, right? That you call as u tilde, suppose.
Okay, sir. Then
And then
what?
find its inverse image under A. That will be your solution. See,
Okay, sir.
generally what you do is, what do you mean by solving a system? This is A, this is your Rn, this is your Rm, right? This is your element B. So you will find an element here X such that Ax goes there, right? This is a general protocol. What do you mean by Ax equals to B? This is a pictorial representation, right? X will map to B under map A, right? This is the meaning. But if B is not in the range space of A, then you cannot find. Then there is no such element X here which will map to B, because B is not in the range. But what you do is you take the best approximation of B in the range space, call this U, and then map this guy to, then find the inverse image of that projection, or what is the best approximation, and that will be your least square solution. I'll express everything in, what do you say, a nice theoretical form so that you will understand more. Just give me a minute now.
Sir, so the solution is called a least square approximation.
Least square solutions. Yeah, here what the u you are getting is called as best approximation, and the inverse image x that you will find in Rn is called as the least square solution.
Okay, sir. Thank you.
Now I'll express everything in writing. You want to find, in straight terms, x belongs to or u belongs to Rn such that norm of au minus b is less equal norm of ax minus b for all x belongs to Rn. You must have seen this equation in the lectures, right? This inequality. This is called minimizing norm ax minus b. You want to minimize norm ax minus b and then find such a u, right? You want to minimize this thing. If b belongs to range of a, then what is the solution? Because simply there exists some u such that au equals to b, right? That's the definition of b being in range of a. If b is in range of a, then there exists u such that a equals to b, then simply au minus b is 0. And then it satisfies this equation. Right? I will name this as equation number star. So for any element in range A, its pre-image will be your what do you say, least square solution. But now if B is not in the range, now let's say call W be your range space of A, right? Now comes the theory of best approximation. Recall what I explained just now. See all these things. best approximation. You have a B non-linear space, W a linear subspace, then you can find an element U in the subspace such that norm X minus U is less equal norm X minus W for all W belongs to capital W. Right? So in this sense, if my W is range space of A, then norm AX minus B, sorry, AU minus B, I want this thing, this equal norm AX minus B, but I will write this AX as U tilde. I want this to be less than W minus B for all W belongs to range of A. Right? This is equivalent because every element in range of A can be expressed as AX for some X, and I want such an element U tilde. Right? This U tilde also belongs to range space of A. Now this is an equivalent condition. Right? So what this has to be, so AU, this implies AU has to be U tilde, right? Or in the previous notation that I have mentioned, AU has to be PB, right? Projection, this PB that I defined. Where I define PB, yeah, here. Okay. Okay, so I'll explain with an example now. Right. Okay. A be this matrix 1 minus 1, then minus 2, 2. Okay, this is my matrix A. Now take B as 1, 0. Now tell me, is element B belong to the range of A? Can anyone tell me
Yes,
yes?
sir.
Yes. Sorry, I couldn't hear you. Can you repeat?
Yes, sir.
This 1, 0 belongs to the range of A, is it? Then can you give me a pre-image?
Not belongs to range space of it.
What? This element B in fact does not belong to range of A. How do you check that? You want to solve the system Ax equals to B and see if it has a solution or not. Okay. So what is the system? Minus 2, 2, then 1, 0. Right? Then you reduce into row echelon form. Minus 1 plus 1, 0. This R2 changes to R2 plus R1. Then you get 0, then 0, then 1. See, the rank of this matrix is 1, but the rank of combined matrix is 2. And the system does not have a solution. Right? But this is imply B does not belong to range of A. Now what is PB? For that you need W. W is range of A. What is range of A? It is span of the element 1 minus 1. And if I want to take orthonormal basis, it is root 2. Right? Because range of any matrix will be its column space, right? The first column is 1 minus 1, second column is minus 2, 2. So I can take the linearly independent column 1 minus 1 and I take a normal vector so that I divide it by its norm. So W is range of A, which is span of 1 minus 1 upon root 2. This is my W. And I define the projection PB, which is inner product of B with this element 1 minus 1 by root 2 into 1 minus 1 by root 2. What is my B element here? B was 1, 0. Which is simply, yeah, 1 by 2 minus 1 by 2. Right? question reduced to solving AU equals to PB, that is matrix A, U, I will call this U as U1, U2 equals to PB, which is 1 by 2 minus 1 by 2. So this implies 0, 0, 0, 0, which implies U1 minus 2U2 is equals to 1 by half. This is the condition, right? Okay. Remember, what is this condition? Set of all U such that AU equals to PB is same as space of all U1, U2 such that U1 minus 2U2 is equals to half. Okay, so now we are halfway there. What we did is, if I do a recap, this was my A. This is A, this is B. I want to solve the system AX equals to B, but B does not belongs to range of A. So the pictorially what we have is, we have here R2, here also R2, and the range here W is this guy here, which is span of 1 1, or this I'll call range of A, and my element B belongs here 1 comma 0, right? What I did is I took its projection in W, which was my element 1 by 2 comma minus 1 by 2, this element 1 by 2 comma minus 1 by 2 was the projection of B 1 0 onto the range of A. Now I want to find all elements here, right, U, such that their image is this 1 by 2 comma minus 1 by 2, right? Set of all U belongs to Rn such that AU is PB, which is 1 by 2 minus 1 by 2. This is this subspace. Okay, is that clear?
Yes, sir.
Yeah. Now let's see the surprising fact. The A matrix is 1 minus 1 minus 2 2. What is A dagger? Moore-Penrose inverse of A. Can anyone compute the Moore-Penrose inverse of this matrix quickly? Or maybe I'll just leave it for you as an exercise, but I give you what is A Moore-Penrose inverse directly. This is 1 by 10, 1 minus 2 minus 1 2. Now if you calculate A dagger B, 1 by 10, 1 minus 2 minus 1 2 times the B vector, which is 1 0, you get here 1 by 10 and then minus 2 by 10, right? Now does A dagger B belongs to this set? Okay, the set I just now defined. U belongs to Rn such that AU is equals to PB. I'll call this set as A inverse of the element PB, right? That's what I did. I take the element PB and I take all its inverse images under A, right? So the question is, does A dagger B belongs to A inverse PB? So let's see. What is A inverse PB? We have just seen the set of all U1, U2 says that U1 minus 2 U2 is half. So what is here? The U1 is this guy, U2 is here. So what is U1 minus 2 U2? 1 by 10 minus minus plus 2 to the 4 by 10, which is 5 by 10, which is 1 by 2. See? U1 minus 2 U2 equals to 1 by 2. That means A dagger B belongs to A inverse PB. Right? That means what? A dagger B is the least square solution. A dagger B is the least square solution of system AX equals to A. Right? That's not a coincidence. The whole definition of the Moore-Penrose inverse defined like this. You take, okay, I'll write on the new page. Analytical definition of Moore-Penrose inverse. Take any B belongs to, let's say, Rm, or I mean, if A is an M cross N matrix, let A M cross N, hence this will map Rn into Rm. So take any B belongs to Rm, define B from Rm to range of A with the projection. In bracket, that will give you the best approximation as I have defined earlier. Now, what you do is you consider A inverse of the element PB, right, which is set of all U belongs to Rm such that AU is PB, right? The points to notice is if P belongs to Rm, the node points, if B belongs to range of A, then PB equals to B, right? That's what a projection means. It acts identity on the range space, right? So if B belongs to the range, then then the set only becomes a set of all U such that AU equals to B, and if A is invertible, then this A inverse PB, which is same as A inverse B, is singleton set, right? Because you get only one big image if A is invertible, right? But if A is not invertible, then the set of all inverse images can be like infinite. Okay, it will be infinite. So now we consider this set A inverse PB is A inverse PB is convex closed set subset of Rn. So any convex closed subset of Rn has an element with least norm. And that element will be your A dagger P. We define A dagger B as the element of A inverse PB with least norm. That is, how are we defining? A dagger B is defined as an element which belongs to A inverse PB such that norm of A dagger B is less equal is less equal norm U for all U belongs to A inverse PB. Okay, this is a precise analytical definition of how a Moore-Penrose inverse is defined. If I again give you a pictorial definition, this is your B. You map this B in here. This is your PB. Then you take this is your singleton PB. You take its inverse image. This set is your A inverse PB. And then in this set, you find an element with least norm. This is your A dagger B. Okay, this is how you went. You went from this A to this element, this A dagger B, right? This is how your Moore-Penrose inverse is defined analytically. For every element B in Rm, right? This B was in Rm, and this here A dagger B is in Rn, right? So this is kind of a inverse map. A goes from Rn to Rm, A dagger will go from Rm to Rn, right? This is how the whole theory of Moore-Penrose inverse is defined. You don't have an inverse of A because A is not bijective, then you have a Moore-Penrose inverse, right? And those both will be the same when A is bijective. You can see if B if A is bijective, then the range space will become the whole Rm, and the projection will be the same, and the inverse image will have only one element, that will be your A inverse B. Okay, is the whole analytical representation clear of the Moore-Penrose inverse?
Yes, sir. Sir, can you repeat the note you have written?
What?
Note, sir.
Note. Okay.
Yes.
Yeah. See, if B is in the range of A, then then projection will be the same, right? So projection means what? You find an element in the range space which is closest to that point B, right? And if B is in the range space, then which element is closest to B itself, right? It's like saying there are a bunch of people in a room, and there is a person outside the room. So you want to find a person in the room which is closest to that person outside. So that you can find if the person is outside. But if the person is inside the room, then that person himself will be closest to him, right? Do you understand the logic?
Yes, sir. Yes.
Yeah, that's what it says. If B is in the range space, then projection becomes itself. PB is B, and then you can find only the inverse image of B directly. And if A is invertible, then what are the inverse images? You can only get one inverse image, right?
Yes, sir.
Yeah. So in that case, A dagger B will be same as A inverse B because it's the singleton set.
Okay, sir.
So that's how when A is bijective, Moore-Penrose inverse coincides with your usual inverse. Okay. So now, as a recap, what we understood is the whole Moore-Penrose inverse theory is regarding finding a least square solution to the system Ax equals to B, right? So let's formulate it in a different way again.
So please write the spelling of a dagger, sir. The symbol.
What do you want me to write? Spelling.
Yes, sir. Spelling of this symbol dagger, sir.
This is your simple dagger.
Okay, sir. Thank you.
Okay. Now what I'll do is, what we have seen is A dagger B will give you a least square solution for system Ax equals to B, right? Another way of finding this is a following theorem or a proposition. Let A is from Rn to Rm be a linear map. Then following are equivalent. First thing, that be a linear map, and let's say an element B belongs to Rm. Then following are equivalent. Number one, U is uh, least square, or I'll write it in the mathematical form, norm of AU minus B less equal norm ax minus b for all x belongs to Rn. Right? What is inverse meaning of this first statement? U is the least square solution for the system ax equals to b. Right? Now, equivalently, in the second line, what do you get? As we have seen before, this is equivalent in solving the equation AU equals to PB, right? Where PB is the best approximation of B in range of A. Now equivalent in the third condition is just finding A star AU equals to A star B. This is the interesting property. This is an interesting one. So 1 and 2 we have seen before, that I have just showed now that in order to find a least square solution U, it is enough to find the element which satisfies this AU equals to PB. Okay, the least element in this set. Now we'll see how these two are related to option number 3. Okay. Before that, I'll give you an idea by an example, the same example that was before. What was your A? It was 1 minus 1, then minus 2, 2. Then let's calculate its A star A. A star A will give me 1 minus 2 minus 1, 2. And then 1 minus 1 minus 2, 2 will give me 2, then minus 4, and then minus 2 minus 2 minus 4, and then plus 8. Is it correct? Oh, I hope so. Yeah, okay, this is correct. So I want to solve A star A. So what I want to solve? A star U equals to A star B, right? What is A star B? A star is 1 minus 2 minus 1 2, and B is 1 0. I want to solve 1 minus 2. So the equation uh, to find least square solution of Ax equals to B, that was our first problem, right? Question number 1, we were interested in this question, and we got kind of a solution as finding least element in this set, right? Set of all u1 comma u2 such that u1 minus 2u2 was 1 by 2, right? This was our answer. Yes, this is the set. Well, it was P inverse PB, A inverse PB that we call this set, and then we wanted to find the least element in this set. That was the answer, right? So now let's see what this will give us. A star AU equals to A star B. Now if we find this set, A star A is 2 minus 4 minus 4 8, and U, just a minute. Yeah. So A star AU equals to A star B. So A star B is the element 1 minus 2. 1 minus 2. So if you want to solve this, 2 minus 4, 1. And then I'll change R2 to R2 plus 2 times R1. I'll get minus 4 plus 4 0, 8 plus 8 0, minus 2 plus 2 0, which implies 2u1 minus 4u2 is 1. This is equals to u1 minus 2u2 equals to half. See, the sets are same. So the initial question to find least square solution of Ax equals to B give us this set, and even the solution of this equation A star AU equals to A star B also gave you the same set, right? So this is proposition. This is what this proposition says, that this finding a solution of any of these three equation 1, 2 or 3 is the same. Okay, so this is magical, right? Ax equals to b need not have a solution always, but a star au equals to a star b always has a solution. What I'm saying is ax equals to b may be inconsistent, but a star a, I can write x again, equals to a star b is always consistent. And the solution, let's call this as equation number 1 and this as equation number 2, and the solution to equation 2 will give you a least square solution to equation 1. Is it clear?
Yes, sir.
Yes. So can anyone prove me or tell me why is this system always consistent? A star ax equals to a star b. Now I want to prove that the system a star ax equals to a star b. This system is always consistent for any b you take in Rn. Okay, let's see. See, I want to show a star ax equals to a star b is always consistent for
Sir, is it happening because of orthogonal property? Orthogonal property.
yes, yes, yes. You are partially true, but you have to explain it properly.
Sir, orthonormal.
Oh, no, what is this? Orthonormal is not a property. I mean, what do you mean by orthogonal property? Okay, let's say I'll explain what this thing is. See, I want to show a star ax equals to a star b has a solution. That is, if and only if I want to show that the range are same. The range space of a star a is same as, okay, instead of r, I'll write range of a star a is same as range of a star. Right? If I show this, then I'm done. Right? The first part is easy. See, the range of a star a is definitely contained in range of a star, right? Because you are having a star at the left. So whatever is the range of a star a is anyway is contained in range of a star. The only thing we have to prove is the reverse part, right? So you have a subspace here, which like this is a vector space you can consider, and this is a vector subspace you can consider. I want to show that those are same. It is enough to show that their dimensions are same. Right? So I will use rank nullity theorem. to show the dimension of range A star A is same as dimension of range of A star, right? So first of all, A star A, first of all, A is a map from Rn to Rm. A star will be a map from Rm to Rn, and A star A will be a map from Rn to Rn. Okay, so this makes sense. Talking about range of A star is in Rn and A star A is also in Rn. So this everything makes sense, right? Everything is in the same codomain. Now what I'll know is claim 1, null space of A star A is same as null space of A. Is, yeah. Okay. Yeah. I will prove this one. Right? From these three equations here, what I get is see, from rank nullity theorem here I get n equals to rank of A plus nullity of A. Here I get m is equals to rank of A star plus nullity of A star. Here I get n is equals to rank of A star A plus nullity of A star A. Yeah. So let's just combine this one and this one here, first and last. So if I show that nullity of A star A is same as nullity of A, then what I get? N is the same, then I ultimately get rank of A same as rank of A star A. But rank A is same as rank A star, hence we are done. Right? So the only thing I have to show is this thing. Null space of A star A is same as null space of A, then I'm done. So let an element X belongs to null space of A. This will imply AX is 0. Then this will imply A star AX is 0. Right? Because 0 element will always map to 0 element under linear transformation. This will imply X belongs to null space of A star A. Right? So one side is done. That means what we have proved is null space of A is contained in null space of A star A. This is done. Other part. Now let X belongs to null space of A star A. This will imply A star AX is 0. Right? Now consider inner product of, or let's consider norm AX squared. I know this can be written as inner product of AX with AX, but then this is inner product of X with A star AX, and I know A star AX is 0. Inner product of X with 0 is 0. Hence norm of this element is 0, which implies the element is 0. But then this will imply X is in null space of A. So I got other part also. I started with an element in null space of A star A. I ended up in an element of null space of A, which implies null space of A star A is contained in null space of A. Right? So this is kind of, now I don't know how many equations are there, but the
Sir,
question 3, question 4, yeah.
sir, instead of using inner product here, can we pre-multiplying by A, sir, here?
Where here?
Sir, in this second claim, sir, let X belongs to an null space of A star A implies pre-multiplying by A, sir, here, both sides.
You are saying here, right? The one I circled.
Yes, sir.
So if you multiply with A, you get A star, AX is 0. So now,
So we say here A star equals to identity, sir?
no. Why? A is not a unitary matrix or orthogonal matrix. How can you say A star is identity?
Okay, sir. Okay.
3 and 4, what we get is null space of A star A is same as null space of A. That means nullity of A star A is same as nullity of A. Then that will prove rank of A star A is same as rank of A, which is same as rank A star. Column rank and row rank will be same, right? If this is true, then we are done. Then A star A x equals to A star B is always consistent. Okay, so the overall theory is what I explained is everything revolves around solving the system Ax equals to B. If B is not in the range of A, what we need is we want to find a least square solution for the system Ax equals to B. Then finding a least square solution to system Ax equals to B is equivalent to finding any of the solution to these three equations. And a solution to all those three equations will be given by the Moore-Penrose inverse A dagger B. Solves 1, 2, 3 equivalent. Okay, the theory behind everything is given in these notes. Okay. This is how the A dagger B is defined. Also now some authors define Moore-Penrose inverse in the following way. For any matrix A belongs A m cross n, a matrix X which is n cross m, which satisfies the following condition. Number one is AXA should be A, XAX should be X, AX star should be AX, and XA star should be XA. So if X, a matrix X satisfies these four equations, then X is called as Moore-Penrose inverse. The same thing. This is an algebraic definition. That one was analytic definition. X is called Moore-Penrose inverse of A. Okay. If you notice here, I have given the solution, that is A dagger B, which will solve equation number 3, right? If you remember in such lectures, if A star A was invertible, then this is simply U equals to A star A inverse A star B. So that if A was a full rank matrix, if you remember the column rank was full, then this is what Sir defined as the Moore-Penrose inverse, right? The A dagger B will be this A star A inverse into A star B. Instead of star, he took transpose because everything is in real, right? So everything boils down to Moore-Penrose inverse. I hope this whole Moore-Penrose concept is clear to you. It's a bit complicated, the theoretical aspects, but I thought you should know this thing. This Moore-Penrose inverse is a very trending research topic. There are several problems available in in the general inversion theory, and this Moore-Penrose inverse is one of the topics. So feel free to explore the area and jump into some problems if you want. If you have any doubts, you can ask, or we can end up for today. In the next session, I will explain. Next session will be a last session, so I will be explaining more sample problems, which will cover the whole theory that was covered in the course. If you have any doubts, you can ask.
In last theorem, we proved that, sir, null space of A star A equals to null space of A.
Yeah?
Implies rank of A star A equals to rank of A star. Sir, then implies system is consistent. Sir, can you explain? I forgot.
See, what does it mean by rank of A star equals rank of A star? That means the range spaces are same, right?
Yes, sir.
Range of A star A is same as range of A star, right? Now what is my system? A star AX equals to A star B. Now this element A star B belongs to range of A star, right? Just it looks like simply it's A star B. So
Yes, sir.
it of course belongs to range of A star. That implies A star B should belong to range of A star A also because they are same. Now, what is the meaning of an element belonging to range of A star? That means there exists some x belongs to the domain Rn such that A star Ax equals to this element here, which is A star B. And that is what meant by system being consistent.
Okay, sir. Got it, sir. Thank you, sir.
Yes, Suraj Pathak, you have a doubt? You raised your hand.
Yes, sir. So last topic, more preserving of a where x n cross m is
Yeah,
what is x n cross m.
that's the order of the matrix.
So
Yeah,
then
if in case A was 3 cross 2, then X will be 2 cross 3.
in previous example,
Yes.
b equal to 0 1 we take here.
No, no, no. B has no role here. These are matrices. Like, see, if A my in previous example my A was 1 minus 2 2, right?
Yes, sir.
This is a 2 cross 2 matrix. Hence M and N are same. So my X was 1 by 10 1 minus 2 minus 1 2. If you remember, this was my X there, which is also called as A dagger.
Yes, 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 sir.
Yeah. So, but if this A matrix was, let's say, something like 2 cross 3, like 2 1 1 0 1 0, something like this. Yeah, this is a 2 cross 3 matrix. Then A dagger, which is X in this whole scenario, will be a 3 cross 2 matrix. Like something like 1 2 3 1 1 minus 1. I mean, this is not A dagger. I'm just saying as an example. Okay.
Yes, sir.
Yeah, this is what it means by N cross N. Okay.
Yes, sir.
Sir, in the last lecture, we have three doubts were left, sir. So,
Yeah, so I have seen those. The first doubt you had was what is the meaning of ill-conditioned systems. Yeah. So I have watched the lecture series. Sir had explained this thing in very much detail. What means by an ill-conditioned systems. You can refer to the lectures. I don't think any other meaning is required because the whole ill-conditioned systems is a complete algebraic topic. You just have to solve system x equals to b, and if you make any changes in either the right hand side vector b or coefficient matrix a, then how much change in x you can expect. So he also in fact derived the formula how you get that condition number, which is what is it, sigma 1 by sigma n, or norm a into norm a inverse, right? That's what he defined. So you can refer the whole lecture, and I think that's sufficient meaning for an ill-conditioned system. And other doubt, was there any other doubt? I don't remember any other doubt. Yes, Ramya, you have any question? So regarding the ill-conditioned system, I will suggest read the lecture videos. I mean, watch the lecture videos again, and you will get an idea. Yes, anyone was speaking?
sir, I have another doubt, sir.
Yeah, please tell me.
Sir, for verify a set is a vector space or not, we check two properties: vector addition and scalar multiplication, sir.
Okay, you want to check whether a subset is
Sir,
a subspace or
so
not.
Sir, so, sir, I want an example of that in which scalar multiplication hold and vector multiplication doesn't hold, sir.
What do you mean by vector multiplication?
So, vector addition, sir. Sorry, sir.
Okay, so you want an example where scalar multiplication holds, but
Not vector addition, sir.
okay. So take. Okay, you can find an example. Maybe in R2 you want. Yeah, in R2 you take the set V, or let's say W, to be kind of in graphically union of these two lines. Okay, so this is the line y equals to x. Let's say this is the line y equals to 2x, right? So if you take any point in this set, I mean union of these two lines I'm taking, okay? In every point on this line, union every point on this line. This is your set W. So how do I write this? W is set of all x comma y such that y equals to x or y equals to 2x. This W will be a union of these two lines. Now if I take any element in the set, right, uh, let x comma y belongs to W, which implies either y equals to x or y equals to 2x. But if I multiply by alpha xy, what will happen? What is the y coordinate of this new element alpha xy? Alpha y, but because y equals to x, this is same as alpha x, and because y equals to x, alpha y will be same as 2 times alpha x, right? So this will imply alpha times x comma y again belongs to W. Here also alpha times x comma y again belongs to W. So scalar multiplication always holds, but you can of course give an element 1 comma 1, let's see here, and 1 comma 2, let's say, which is here. What is addition? Which is 2 comma 3. This element is neither on this line neither on this line, it is somewhere here. Okay,
Yes, sir.
because the y coordinate is not same and not also twice. Do you get an example here?
Yes, sir. Got it, sir.
So if you have any other doubts, you can ask. We're done for today. Yes, Suraj Pathak.
In previous assignment, any matrix can be defined. We can define a positive define and negative define. Then indefinite how to define. Hmm.
I don't understand your question.
In previous assignment 4, one question is a quadratic form something. Then option are positive define, negative define, or indefinite
Okay.
form. Then we how to matlab, how we can define indefinite form.
Okay, there was an option which is called indefinite form.
Yes, yes,
Indefinite means, yeah, indefinite means, yeah, the Sonia Thakur has explained. It's a matrix which is symmetric, which has both positive and negative eigenvalues. See, for a positive definite matrix, eigenvalues will be positive. For a positive semi-definite matrix, eigenvalues will be strictly positive. For a negative definite matrix, eigenvalues has to be less equal 0. But for an indefinite matrix, it has both positive and negative eigenvalues. Is it clear? The meaning of indefinite matrix?
yes, yes.
Yeah. Yeah. So, any other doubts? Yeah, again, Suresh Pathak and Deepesh Meena. Okay, raise your hands.
Hello, sir.
Yeah, yeah, please. I can't hear you. I can't hear you. There is some noise problem in your side. I can't hear you. Can you maybe repeat?
Hello, sir.
Yes. Yes. Hello. You can even type in the chat box if there is some audio problem there.
Hello, sir.
Yeah, I can hear you now.
Sir, is there any blueprint of question paper?
Blueprint of question paper? No, no, I don't think so.
Some sample paper?
Sample papers, we can ask NPTEL team. I mean, I don't have any rights for that. So you can
Okay,
maybe
sir.
ask NPTEL team if they can provide any sample papers to you, then that will be beneficial, I guess. Yeah. So, Sonia Thakur has a question: how to compute rate of convergence of P, where P is Jacobi iteration matrix or Gauss-Seidel iteration matrix? I don't have any idea about this. Is it not explained in the lecture videos? I hope so. It should be explained. Calculating the rate of convergence, because you have to precisely define what is the rate of convergence there, and I haven't seen those videos yet. Okay, if uh, have you seen the lecture videos? Because if not, maybe you
Yes,
see.
sir.
Yeah.
Lecture.
Yes. Maybe then I'll watch and then I'll explain the next session what if there is some confusion regarding rate of convergence of the matrix P. Okay.
Sir, this topic is explained in the lecture, sir.
What?
Sir, this rate of convergence of a matrix explained in the lecture, sir.
Okay. I'll explain this. Yeah, how to find fundamental matrix and its properties. What do you mean by fundamental matrix? Suraj Pathak, you had asked how to find fundamental matrix and its properties. Can you tell me what is a fundamental matrix?
First of all, find out eigenvalue, then we can find eigenvector with respect to eigenvalue.
Yeah.
Then its determinant
Then
eigenvector determines is known something some is fundamental matrix.
from eigenvectors you create the matrix P and that you call as a fundamental matrix. Is it?
Yes, is this type.
Then you just have explained me how to find a fundamental matrix. What's your doubt?
Property. What is property? Fundamental matrix.
So, okay. As far as I understood, you have a matrix A. You find its eigenvector. You find eigenvectors and put those in columns. Let's say maybe columns of P, and then this P is your fundamental matrix. Is it?
Yes.
Then there are no such specific properties about P. Fundamental matrix. Is it just a matrix? If you have n linearly independent eigenvectors, then if you do P A P inverse, you will get a diagonal matrix D which consists of an eigenvalues of A. So, but other than that, I don't see any properties of P specific properties for P. I don't even heard this name fundamental matrix before. So, even I don't think so. There has to be some any interesting properties regarding this matrix P. Yes, Dipesh Mina. You can ask your question.
Yes, sir. Sir, I have doubt in week 7 and weekend assignment. Sir, there is two questions, one in week 7 and one in week 8. I did not get answers for that. Matlab, I think the questions are wrong, sir.
Okay, what's question 7?
Question number 1 in week 7 and question number 3 in week 8.
1 in week 7
Uh, 3 in week 8.
and okay, I'll see these questions and maybe I'll explain in the next session.
Sir, in tomorrow we need to submit week 7 assignment, sir.
Oh. So do you
Then
think the
what I
question?
need to do?
Do you think question 1 is wrong in week 7? Is it?
Yes, sir. The answer is coming. I got my answer, but there is no, that is answer is not in option, sir.
I have to see what question is in fact
Or
now.
and so my 30 classmates all did it. I same answer we got. Can you try now? If I send you.
Question then maybe we can try what.
Yes, sir.
This
Yes.
this
Sir,
is
question
That
regarding
is
what?
based on. So based on list square, sir.
Least square solution is it?
Yes, sir.
Yeah, okay, tell me the question.
The system is x1 plus x2 plus x3 equal 1.
Okay.
Second equation is x1 plus x2 minus 5x3.
Minus 5x3.
Yes, sir.
Yeah.
Equal minus 2.
Minus 2.
Yes, sir.
Okay,
We
so
need to find least square solution.
okay, we want to find least square solution. So in this case, your matrix A will be simply 1, 1, 1, then 1,
Yes, sir.
1 minus 5, and your B is 1, comma minus 2. You want to find the least square solution for the equation system Ax equals to B, right?
Yes, sir.
So simply just find the Moore-Penrose inverse A dagger, and A dagger B will be your answer, isn't it?
Yes, sir. I find it, but I got another answer. My answer is 1/4, 1/4, and 1/2.
Let's see. In fact, we can do all these things in MATLAB if you don't know. I can show you that thing here. So let's say we can put the matrix here. Okay. Yeah, just give me a minute, it's loading. So what to do is you put matrix. What was the matrix? Now we got 1, 1, 1, 1, 1, right? In the first row.
Yes, sir.
And what was the second row? It was
1, 1.
1, 1, then minus 5 is it?
Yes, sir.
Minus 5. So I just want to find its Moore-Penrose inverse. Yeah, the Moore-Penrose inverse I got is okay something this matrix, but I need to multiply this where it's star with the matrix B. Okay, I'll define what B is. B is equal to the B matrix was what? 1 comma, I don't remember that.
Minus 2. Minus 2.
Column, right? 1 minus 2. Okay.
Yes, sir.
1 and minus 2. Okay, so I need P inverse of A into B. I need to calculate this. Let's run again. Yeah, so the answer is 0.25, 0.25, 0.5.
I got this.
This is the correct answer. Yeah, so the answer you got, it has to be 0.25, 0.25 and zero point 0.5. So in other
Yes, sir.
words,
I got same, but sir, this is not in option.
this is not an option.
Yes, sir. Options are, sir, other than this.
Then you can email that NPTEL team, okay, so the course instructor also, and the NPTEL team also that the option in quiz 1 is wrong, and you can attempt anything, they will give marks. They have to give marks. Okay? So this checking quizzes and all is not in my hand. So you have to email uh, what is the course instructor and NPTEL team. You can refer to them that the TA has solved the problem even in the class and he found the same answer and the question does not provide the similar option, so we should be awarded as an marks. Okay.
Okay, sir, I mail.
Your answer is
Sir,
complete.
sir, I have one or week three. No, sorry, week 8 in question 3.
That I'll see. Now tomorrow is not deadline for week 8, right? I'll see that
Yes,
question.
sir, sir. Okay, sir. I will ask in next session, sir.
Cool.
Okay. Thank you, sir.
Yeah, okay. Okay then. So if there are no further doubts, let's meet on next Tuesday.
Okay,
Sir,
sir. Thank you.
sir, if possible, sir, I have doubt.
Yeah, please.
Sir, I mail regarding this, and sir, if we all get marks for this or not, sir? The question is wrong, sir.
You have to. I mean, you should get marks. It's on them. You can email them. I will also try my best to contact some NPTEL team and tell them that this is the thing. But probably you should get marks.
Sir, I think question will be removed, sir, from the assignment. I think in
Okay,
other
marks.
subjects, sir, if a question was wrong, then total marks are for correct questions, sir, not for wrong.
I don't know how the marking scheme works, but you it will be just I mean you will get the justice in some way, like you won't be remove I mean the marks will not be cut from your side. Either assignment A7 will be of only 9 questions, the one question will be removed completely, or they will provide full marks for that particular question to everyone. So in both ways it's the same, right? So one of these can this will happen.
Yes, sir.
Yeah.
Sir, what is the AOC exam pattern for final exam?
No,
I
no,
think I don't have.
I don't have any idea about that.
Sir, this is my first course in NPTEL, so have no information regarding this, sir. Can you little bit give me information?
No, I can give you, but I don't have the information. That's the thing. Maybe you can ask the NPTEL team for this again. As someone have asked just some time before that you can email them asking some sample papers of previous years. From that you can get idea.
Okay, sir. Thank you.
Yeah. Okay, then if there are no further doubts, let's meet next Tuesday.
Thank you, sir.